Hello, and welcome to another one of Ethan's engineering videos. Today we're going to be tackling Homework 2, Part 4, which is going to be the first part in the chunk where we're going to be looking at solving functions for their roots, and we're going to be looking at two methods in particular today. Later on we're going to cover a third, which is a lot more both interesting, but also efficient for large complicated functions. But today we're going to settle on two pretty easy ones. The first one's going to be secant method. The secant method, not really secant. Secant is a noun, not a proper noun, so there's no apostrophe s. And the second one being Newton's method. Newton being the proper noun, and also the famous mathematician who pretty much knew all of the math for his time, because he invented all of the math for his time, because he's a baller like that. But anyway, obviously we're going to have to make a function in order to evaluate it, so that's where we're going to be starting. I've already imported all the stuff we're going to need throughout this entire chunk, so there's kind of some advanced stuff we're obviously not going to be needing today. The only thing we're going to need right now is NumPy, and only in a very limited capacity to easily generate arrays to plot, and Plotly to plot it, because I'm going to show our function after we make it. So to start, we're just going to define our function, since we're going to be define func. And we're going to just take in an x value. Now all we need to do is return some function. So we're going to return like 0.2 times, and then parentheses, I don't know, x, we'll look at the smallest one, so x plus like 0.5, maybe, times x minus 0.2 times x minus like 0.9 or something like that. How will that look? So yeah, if we just run func, if I say 0, what will I get? Okay, pretty small number. What about 1.24? That works for me. So now we're just to show you what it looks like, so I can kind of explain the methods visually and have it actually make sense. Let's plot it up. So we're going to do xplot, and we need to np.linspace. We're going to go from -2 to 2. And we're going to have 101 numbers on there. Yplot is just going to be running our function with all of our values of xplot. And then all we're going to do is create a new figure and put the graph on there. So not fog. Fig1 is going to be equal to make subplots. And then fig1 dot add underscore scatter. I'm going to do x is equal to xplot, y is equal to yplot. Mode is going to be equal to lines. And I set a template here. Template is going to be equal to, okay, so we can't, it's going to just import some random template. That's not what we want to do. I guess we'll just go fig1 dot update layout, and we're going to say template is going to be template. It's going to be equal to plotly underscore dark. IGHT is going to be equal to 600, and then our width is going to be 600 as well. So this is just kind of our standard plotting stuff. This is just so we can actually see what our function looks like. I kind of wish it were taller, so maybe we're going to move you back a bit to like 0.8 then. There we go. And what if we move you to like minus like 1.2 to spread them out a bit? There we go. Okay, so now we can very clearly see where our function crosses 0. Right there, there, and there. We've got 3 of them. So now there's a pretty good time to explain what secant method is and what Newton's method is. So secant method is like a pretty basic thing right here. So we're going to just pick 2 points above and below a 0. So this one's in the negative realm, so we'll just pick like -1.36, and we'll go up here to our top like -0.4, which is a positive value when you do f of -0.4. And so obviously, if you were to draw a line between this point and this point, it would go directly between them, and it would also cross 0, because we're going from a negative number to a positive number And if we're doing it in a straight line with no discontinuities, it has to cross 0 at some point because it's continuous. So essentially what you do is you say, well, across this whole line, the slope is constant. So any 2 points on that line, when compared their slope, when comparing any 2 points on that line, the slope that connects them must be the same slope. So we can calculate the slope between the 2 points that we know, and then keeping one of the points that we know, we imagine what a point on that line would look like. Not imagine, because it's a line we can solve for. We would say, well, what x value on this line that we just generated between these 2 points falls with a y value of 0. So you can back solve for that new x point, and then plug that into your function and say, oh, well, we hit 0 around here, so if we go up, well, that's a negative 0.56. So now you've got a line that connects like this. So you do that again, but you keep 0.56 this time, and this new line is a bit steeper, so that one crosses 0 over here. So you go here, and it's like, oh, well, it's right next to that, so it'll be a lot shallower of a line. And so eventually you just keep bouncing around until eventually the single line bounces back and forth and back and forth and back and forth until eventually it does settle on 0. So let's code that up. So what I said first, I'm just going to summarize it to 3 steps. Step 1, make sure you can see it on both cameras here. Step 1 is going to be finding the slope. Step 2 is going to be back solving for x. And then step 3 is going to be doing that iteratively until we get something that's at 0 or within an acceptable range of 0. So we're going to define by starting. We're going to start by defining our secant function. Spell S secant. And what we're going to take is the function we're going to want to take, find the zeros of. We're going to start with some 2 points, x0 and x1. And then for our own cells, we're going to define our max iter, the maximum number of times we want to recursively do this, which I'm just going to pick 50. And then our tolerance. So how close do we want to get to 0? And I'm going to go with 1 e to the negative 12, because that's pretty small. So what is this function actually going to do? How are we going to solve that? Well, first we have to figure out what the values, both coordinates, x and y coordinates of our 2 starting points are. So we're going to just say f0, not fo, f0 is going to be equal to func of x0. And because I'm going to do it in the same line because I'm baller, we're going to do f1 is going to be equal to the function at f1. So we have our 2 starting points. With that slash there. So now what we're going to do is we're going to iteratively, with those 2 points, find the slope, back solve for x, get our new point, and then replace one of our points with that new point and do it all over again, recalculating the slope, and eventually we should settle on 0. So I'm going to do a for loop. So for I in range, parentheses, max iter. Well, first thing we're going to do is calculate the slope. So the slope is going to be equal to f1 minus f0 divided by x1 minus x0. And there we go. And quickly, just to show how we back solve for x, because that slope is constant throughout the whole thing, we know that for some point that gives us 0, we know that this new point 0 is going to give us 0, and that's going to be equal to x2 multiplied by our slope, more or less. That I wrote that horribly. We know that, yeah, that is not true. I was trying to rewrite it in a neater way and just said something that is completely false. So I'll just write it the way I'm supposed to. So the slope stays constant, no matter whether we're looking at point f1 and f0 with the known 2 x's we start with and their their associated value of our function, but that it will also be true for an unknown set of f's and an unknown set of x. But obviously we can't solve for a set of 4 unknowns because there are infinitely many pairs of points on a line that have the same slope as that line. So we're going to specifically look for f2 minus f1, so we're keeping the point f1 divided by x2 minus x1. And the reason we're keeping one of our points is so that way these 2 values are already known because we just found them above, but also because we know we want whatever x2 is, the point we're going to be looking for, to be equal to 0. And when we're equal to 0, that part just goes away. So we now know that our slope is equal to the negative of our f1 divided by x2 minus x1. And so because we know this, we found our slope already and we know what x1 is, we can back solve for x2. So just doing the mental math, we're going to multiply by this over, we're going to divide by the slope, and then we're going to add x1 to both sides. So we're going to have x2 is equal to, it's going to be negative f1 divided by slope. So just to make sure, we're going to multiply this over, multiply by this, divide by slope. We're going to have negative f1 divided by slope, and then x2 plus minus x1 on this side. So then we're just going to do plus x1. So this is going to give us our new x point. So again, if the analogy was we had a point here, we had a point here. We draw the line between them. We say, hey, on this line, the 0 lies right about here, x-y is negative 0.44. So we've just calculated negative 0.44. So now all we have to do is figure out the new y value, which is going to be, for this example, 0.0768. So it's pretty easy to calculate that because f2 is just going to be equal to the function at x2. Easy peasy. So now you might be thinking, okay, we're good. Now we could just adjust it and go again. However, we do have that tolerance, so we want to make sure that if this new point, if the new f2 is reasonably close to 0 and reasonably being within our tolerance, we just want to kind of stop. We just want to output x2 and f2 because we found our 0 and its associated point. So we're going to do a if check. So if the absolute value of f2, because again, it could be positive or negative, is, since again, we're trying to gauge its distance to 0, it'd be the distance between the absolute value of f2 and 0, or the absolute value of the distance between f2 and 0, but since it's 0, it'd just be subtracting 0, so it doesn't do anything, is less than tolerance. We just want to break. So we're going to break out of that for loop. Otherwise, we would put an else here, but we don't have to. But I will just for the sake of clarity. Otherwise, well, what do we want to do? Well, we want to now do this whole thing again, but with our x2 and our x2 and our x1 functions. So all we're going to do is we're going to say x 0 and f0 are going to be equal to x1 and f1. And then we're going to say that f1 and f2 are going to be equal to x2 and f2. This should be, I got myself confused while writing by thinking and talking at the same time. So we're going to take, we have point 0, point 1, and point 2. We're going to set point 1 to be point 0 and then set point 2 to be point 1. And so with that, we can go in here again and just recalculate a new x2 and reassign it. So all of this, I'm going to get rid of that right there. So all of this for loop right there, this will break us out of the for loop. Otherwise, we're not ready to break out, so we have to redo this. But yeah, and then all we're going to do is we're going to keep doing that until, again, either we reach our max iterations or we found something that's close enough to 0 that we're happy with. And then we could just return what we're happy with. So we're going to return, again, remember, this isn't going to do a reassignment unless it is not close enough. So we're just going to return x2 and f2. Here we go. So if we take the secant of our function, and we're going to try to calculate this one right here, which is at the negative 0.8. So we're going to do something like negative 1.2 and negative 0.44, negative 0.44, and I just gave you the two initialized values to run this. F1 is referenced before assignment. What does that mean? How can it be referenced before assignment if it's right here? Okay, what does that even mean? Oh, I did f1 is equal to the func of x1. I was like, what are you talking about? No, it's supposed to be x1. That's a silly typo. I'm sure you guys were screaming at me through your monitors. There we go, and we should get negative 0.8, as we can see from our function. And we do. We get negative, essentially, 0.8. If we were to kick this down to be like negative 18, we might get a good, yeah, there we go. Negative 18 is enough that it basically gets it right back down to negative 0.8 and 0 because it's within round off. The round off error no longer is visible. Now, that's kind of dangerous, because again, once you get to enough bits out, you start running into the difference between those numbers becomes so small that round off errors start like seriously messing it up. So I'm going to set it back down, but in this case we were lucky enough, but I mean this is close enough for a person to realize that this is about 0 and this is about 0.8. So our secant function does its job. Now, the Newton's method is very, very similar to the secant function, but with one crucial difference. With the secant function, you start with 2 points, draw a line between them, find out where 0 is on that line, and then solve for the new x value based off of the slope and the fact that you're looking for the y of 0 for the new x2, and then you redo that iteratively. This one is very similar, except it doesn't use 2 points. So we start with a point, like 1.2. We figure out the slope at that point using just taking the derivative of it. Because, again, before what we were doing, we were using 2 points to find the slope between them. For this one, we're just going to find the derivative at that point. So some line that looks like whatever. Then you're going to follow that derivative until it hits 0. Pick that as your new x. Figure out the x that gave you 0 on that derivative, because you're going to basically approximate this line. You're approximating the function as a line on the tangent line to that point, finding where 0 is, and then using that, taking the derivative of the function at that new x, and again evaluating that over and over until you eventually reach 0. So instead of drawing like a render line or like ray tracing basically between the interior curvature of your loop, because this one would be bouncing on this one and this one would be bouncing down here, what you're instead doing is you're basically following the gradient until you reach somewhere where the gradient is both 0 and the y value is 0. Or not the gradient is 0, the y value is 0, the gradient's not 0. We're not finding a minimum or maximum, we're finding a 0. So it's going to be relatively similar, so we're just going to define this as Newton, and this is going to take our function and an x0, and then I'm just going to copy and paste our max iter and our tolerance, because again we're going to be doing this iteratively, but again we do not need a second one. So we're going to say f0 is going to be equal to the function at x0 once again, and then we're going to build our for loop. So for I in range, let's see, is max iter. What we're going to do is we're first going to figure out what the slope is at our x0 point. Actually, out here I can do that, because we're going to have to do it. No, we're going to have to calculate f prime every time. I'm trying to think, how do I want to do this? Do I want to do f prime every time? Yeah, I'm going to want to recalculate it every time, I think. But if I don't need to, I can just get rid of it then. So we're going to find f prime is going to be equal to, well, it's going to be the jax dot. Oh, actually, I just realized this is going to be a function. It's going to be f prime is going to be a function, not a specific point. So we don't need to calculate it every time. So the grad of our function func. So right there. So we're going to get a function that's the derivative. So again, we're putting in a function and outputting a function. That was what caught me up, because I was thinking that, like, oh, this is going to output the derivative at 0.0. No, it's not. This is going to give us the derivative of our function at any point. So now what we can do is, there we go. I'm trying to think of like the order I want to do this, because there's like, it's fairly simple. I just want to make sure I'm doing it in the best way possible. So yeah, we might as well just calculate. I'm just like torn up on how to do this, because I want to do it in a way that looks pretty and is efficient, but I also just don't want to think about it too hard, because I just want to get this video done. But I'm like thinking about it too much. Okay, whatever. So we're going to basically look at it, and we're going to say that, just like we did before, we know that somewhere along this gradient, because again, we're drawing a new line with the slope of whatever, we know that 0 is going to be equal to, because we're outputting, we're going to do we're going to have the x we're looking for, minus x1, is going to be equal to, I'm like tripping myself up very much. So f1 minus f0 is going to be equal to our delta x. So I'm just going to abbreviate that as dx times the f. Actually, I can use apostrophes of x at x0. This is our approximation right here. So as you can see, this is our linear approximation. So I might want to change this to be approximately. Because obviously when we take f prime at 0, multiply it by our change in x, we're going to get this. But again, we're hoping that f1 will be 0. So again, we're going to get a negative f of 0. And again, this is not going to be actually true. But since our dx, again, is actually x1 minus x0, as we did last time, we can just solve for x of 0, x of 1. So x1 is going to be equal to negative f0 divided by f prime at 0, f prime at x0, plus x1 again. So you can see it's a very similar function to what we did before. And then f1 is going to be equal to function of x1 and then we can just kind of copy this right here. Obviously we're going to change it up a bit because this is all we need is this, and we can change that. So now we're going to look at f1 and say, is f1 close enough to 0? If it is, break. Otherwise, set x1 and f1 to be our new x's. And then at the very end, we're going to want to return x1 and f1. So if I copy this right here, I get rid of the end there, and I tell it to run Newton, spell it correctly. Okay, that's weird. Is this? It's both saying it's completed and it's not completed. Is my runtime listed? Let me just reload the page. I think yeah, I'm gonna reload the page. That's really weird. Yeah, reload. Okay, no, cancel out. Running again. Top. Make runtime. Maybe my internet died. That would be bad. My connection is apparently not super great. I would be so mad if my Wi-Fi died. Wow, it really can't connect. Okay. Oh, okay, guys. I know that about, but what is happening? Why don't you go away? Just reload the page again. Don't care. I want this to be fixed. Okay, there we go. Run from the top. That's so strange. Renew, 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 renew. Unknown variable x1 reference before assignment. Oh, it's supposed to be x0. Silly. There we go. There we go. We found negative 0.8 once again, and we've got something that's basically more or less 0. Now, the other test is if we come at it from the other direction. So we do negative 0.44. And as we can see, we arrive at the exact same root. So our Newton's function also works. So despite that weird 3 minutes with my internet just absolutely losing its mind, This has been a pretty simple and easy to explain success. All we needed were these one little lines to explain what we were doing. This one deals with like the definition of a line with the slope being constant all along a line. And this one deals with just treating the derivative of a point of a function like a line, and just from there back solving for a new x point where the y value is 0. So this has been pretty simple. I hope you guys, stuck through this and could understand what I was saying, despite all my weird tech problems that kind of came out of nowhere. But I appreciate your attention. So thank you, and have a good evening.